Okay, so we're on a roll. We've made it through protons, neutrons, electrons. We've talked about why the electrons are significant. The number of electrons in the outer shell is going to determine an atom's chemical behavior. And remember that these column numbers are kind of a shortcut. So if an element's in column 1, it means there's 1 electron in the outer shell. Column 2, 2 electrons, and so on. Going all the way over to column 8. And anything that's in column 8 has a full outer shell, is inert, it's not going to bond with anyone else. Everything in columns 1 through 7 is going to tend to do something to try to fill that outer shell. Just a couple of quick review questions before we move on to bonds. How many valence electrons does carbon have? So to answer that, you can either look and see that carbon is in column 4. And if you're in column 4, you're going to have 4 electrons in the outer shell. Okay, but let's draw carbon's full electron configuration just to check. So remember, when we show where the electrons are located, it's called the electron configuration. So carbon's atomic number 6. So this is carbon. 2 spots in the first shell. Remember, first electron shell can hold a maximum of 2. Second electron shell can hold a maximum of 8. Again, I draw it this way just because it's going to be easy when we start drawing molecules to show sharing of electrons. Okay, so carbon is atomic number 6. That means it has 6 electrons total. It doesn't have 4 total, it has 6 total. This atomic number is going to tell you the total number of electrons. 6, 1, 2, 3, 4, 5, 6. So how many valence electrons does carbon have? That's asking how many are in the outer shell. 1, 2, 3, 4. Again, it's in column 4. So carbon has 4 valence electrons. How many more electrons does carbon need to have a full outer shell? 1, 2, 3, 4 empty spots. So correct answer again is 4. Carbon needs 4 more electrons to become stable. Remember, every atom needs a full outer shell to be stable. So now things start getting exciting. Now carbon is going to need to do something to fill that shell. Let's look at hydrogen again real quickly. Because hydrogen is one of the guys who carbon can make a deal with and fill that outer shell. So hydrogen was atomic number 1. So looking at hydrogen's situation, 2 spots in that first shell, and hydrogen has 1. So hydrogen's cruising along, comes in proximity to carbon, and guess what? They can share electrons to complete their outer shell. So this hydrogen can come in, and he brings 1 electron to the party. Here's our hydrogen. I'm going to keep his electron red. If hydrogen shares his 1 electron with carbon, and carbon shares this electron with hydrogen, now hydrogen has a full outer shell, and it is stable. And if that happens with 3 more hydrogens, I'm not the best at drawing on the board, as you can see, but you get the idea. One, 1, 1. So each of these hydrogens shares their 1 electron, and then carbon shares 1 of its with each of the hydrogens. And now, rather than these purple ones just orbiting carbon and these red ones just orbiting hydrogen, they are shared. They are now shared electrons. And now these shared electrons orbit both hydrogen and carbon. And it's happening so fast that there's no way we could freeze this and go, nether with hydrogen, nether with carbon, nether with hydrogen, nether. No, they are shared. At any given point in time, they are with both. So these are shared electrons. And when two atoms share a pair of electrons, that is a chemical bond. And it is a very important, very strong chemical bond called a covalent bond. So we're going to start talking about chemical bonds. This is how molecules form. So chemical bonds. The first category of chemical bonds we're going to look at involves sharing electrons, and it's called a covalent bond. Sharing electrons. Sharing electrons so that each atom has a full outer shell. So this shows sharing of electrons. These two electrons no longer belong to this atom or this atom. They are shared. They are going to orbit each of these atoms. And now each atom has a full outer shell. Remember, full outer shell for this is 8. It's not showing the inner shell. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So they each have 8. I actually wish that showed the inner shell as well. Okay, so sharing electrons is a covalent bond. This is the strongest of all chemical bonds. So these are the strongest chemical bonds. They are very, very significant in understanding biology. They're strong. They store energy. They store a lot of energy. Stored energy, you might already know, is called potential energy. Covalent bonds have a large amount of potential energy. And when we break the covalent bonds of our food molecules, we release that energy to drive chemical reactions. We're actually going to package it as something called ATP that you're going to learn about. But that potential energy that's in those covalent bonds is very, very important. They're very strong, they're difficult to break, but when they do break, they release energy. They release this potential energy. So very, very important to understand these, to understand biological processes. Okay, sharing electrons. Two atoms can share one pair of electrons. Sometimes atoms can share 2 pairs of electrons or even 3 pairs of electrons with another atom. So in the world of covalent bonds, we actually have single, double, and triple covalent bonds. So single is sharing 1 pair of electrons. And as you can guess, double is sharing 2 pairs, and triple is sharing 3 pairs of electrons. Let's see what that looks like. Okay, so this would be what we've already drawn, sharing 1 pair of electrons. So in each of these spots, this would be a single covalent bond, sharing 1 pair of electrons. These are double and triple bonds. So you can see here that oxygen shares 2 pairs of electrons with this other oxygen. So now these 8 orbit this oxygen and these 8 orbit this oxygen, and each has a full outer shell. 1, 2, 3, 4, 5, 6, 7, 8. So at any given time, these 4 that are shared belong with both oxygens. And that is called a double bond. By the way, we've only shown covalent bonds so far as the electron configuration. But there are 2 other ways to do it, and they're both shown there. 2 simpler ways to show sharing electrons. One is called Lewis dot, and that's what you see in the top diagram. And in the Lewis dot, I'm going to stick with this molecule up here. You would only show the ones that are shared. You wouldn't show the ones on that inner shell. So we would put carbon in the middle. We would show it sharing a pair of electrons with that hydrogen. one with this hydrogen, and this one, and this one. Okay, so that would be a simpler way to show this thing. Sharing electrons. Sharing one pair of electrons. So that would be a single covalent bond. Even simpler, we can just draw a line between carbon and hydrogen. And that line implies sharing one pair of electrons. So this is also a single covalent bond. So sharing one pair of electrons, you just draw a line. And this is how we will typically draw molecules in this course. It's easier, it's faster, it's how you'll see it in textbooks. But if you are asked to draw the electron configuration for a molecule, you need to show this level of detail. Lewis dot, and then more simply this. We can also just write the chemical formula for this. The chemical formula for this molecule would be 1 carbon and 4 hydrogens. So it would be C and then 4 hydrogens, CH4. The 4 is written as a subscript to show there are 4 hydrogens and 1 carbon. They're all bonded together. If I wrote a 2 in front of this, imagine parentheses. This would be telling you I have 2 of these molecules. Not that I have 2 carbons and 8 hydrogens all bonded together. It's 2 separate of these. So it would be this one and then another one. Not bonded together. 2 separate ones. I would put a full number 2 in the front. I wouldn't write the parentheses. Those are just implied. And the 4 is a subscript number. Just one more example really fast. Okay, this is glucose. It's also fructose and galactose. They all 3 have the same chemical formula. This is telling you that there are 6 carbons, 12 hydrogens, and 6 oxygens that make up this molecule. Doesn't tell you in what order they occur, how they're configured. Just tells you that's the total number of each atom. And this is one molecule. What is a molecule? A molecule is 2 or more atoms bonded together. So 2 or more atoms bonded together. They can be the same kind, as you see in O2, right here on the screen, or they can be different kinds, like CO2. Okay, and then finally triple bond, nitrogen, 3 covalent bonds, sharing 3 pairs of electrons. I already told you that, I erased it, I'm pointing to something that used to be there. I already told you that those bonds, those covalent bonds, store a huge amount of energy, a lot of potential or stored energy. And when we break them, the energy is released. What do bad guys make out of nitrogen? Nitrogen fertilizer. They make bombs. When this triple bond is broken, it's very explosive. Same for oxygen. You've probably seen the fire hazard or explosion hazard stickers on oxygen tanks. This double bond stores a lot of energy. When it's broken, it releases a lot of energy. Okay, so single, double, and triple covalent bonds, sharing 1, 2, or 3 pairs of electrons. The strongest of the chemical bonds we'll study, and really, for this course, very, very important to understand. Okay, so now let's talk a little bit more about this whole sharing of electrons. Sharing. Sometimes 2 atoms will share those electrons pretty equally. So in this case, carbon and hydrogen share those electrons pretty equally. No one's hogging them for themselves. But that's not always the case. Sometimes in the world of sharing electrons, 2 atoms don't share equally. And we're going to talk about those 2 different scenarios because it's important to understand the differences. so this is CH4. By the way, I didn't tell you before, but CH4 is also called methane. It's the simplest of the organic molecules, just one carbon long. We'll talk about that when we talk about organic chemistry. So this molecule methane, carbon and hydrogen are sharing electrons. And I'll go ahead and tell you, they are sharing pretty equally. They both have an equal pull on those shared electrons. No one's hogging them. That's not the case in other molecules. Water is a really good example of that. Good old H2O. Okay, so here's oxygen sharing with this hydrogen and with this hydrogen. So two hydrogens bonded to one oxygen. Subscript number 2, because that 2 just belongs with the hydrogen. This one oxygen. Hydrogen and oxygen don't share equally. And the reason for that is oxygen is a big electron hog. It wants to pull all those electrons closer to it. It's not sharing equally. It doesn't play fair, hogging the electrons to itself. And the reason for that has to do with something called electronegativity. This is a very important concept in biology. It's going to tell the chemical behavior of certain elements that are going to contribute to its chemical properties and cause it to do certain things, especially oxygen. As it turns out, everything on the periodic table has an electronegativity rating. The definition in its most basic form for electronegativity is the pull an atom has on electrons. If you have a high electronegativity, it means you have a strong pull on electrons. So high electronegativity equals strong pull on electrons. Oxygen is very electronegative. Oxygen has a very high electronegativity relative to hydrogen. So what does that mean? That means oxygen has a stronger pull on those shared electrons, and so they're not sharing equally. Let's look at a couple of pictures to show that. First of all, this is the trend in electronegativity on the periodic table. There are charts you can look at that give a number value for each of the elements. Please don't look at that or memorize it in any form. All I want you to know is the trend. The lowest is in this corner, excuse me, and the highest is in this corner. It increases as you move left to right and as you move bottom to top. These guys, remember, don't share. They have full outer shells. They're perfectly happy being by themselves. So we're really talking about these guys. Nitrogen, oxygen, fluorine, chlorine, all have a very high electronegativity. Oxygen being really the most biologically significant one that's highly electronegative. What that means is when they're sharing with somebody who's not in this little corner, they're not going to share equally. They're electron hogs. They don't share equally. If oxygen was splitting an ice cream sandwich with you, he would take 90% of it and give you 10%. He's not going to share equally. Two terms associated with these two kinds of sharing. Okay, so as it turns out, carbon and hydrogen have similar electronegativity. If we were looking at H and H, that would be the same electronegativity. So similar or same electronegativities between the two atoms, that's going to give you equal sharing. Why? Because you have similar pull on those electrons. these two hydrogens have the exact same electronegativity as each other, so they're going to have equal pull on those electrons. So those electrons are shared equally. They're right here in the middle. They're shared equally between those two hydrogens. That's called a non-polar covalent bond. So similar or same electronegativity, equal sharing of electrons. My board's getting a little messy here. That's called a non-polar covalent bond. So it's sharing electrons, so it's a covalent bond. They're sharing equally, so it's called non-polar. Water, on the other hand, oxygen and hydrogen are not sharing equally. And that's because there's a big difference in electronegativity between those two atoms. So big difference in electronegativities. Unequal sharing of electrons. Why is it unequal? Because one of those atoms has a much stronger pull on those shared electrons, not sharing equally. And that is called a polar covalent bond. Polar covalent bonds, polarity, unequal sharing. So that would be like this picture. Chlorine, up in that little triangle, very electronegative. Look how mean he is. He's an electron hog. Poor hydrogen doesn't have an equal pull on those shared electrons. So polar covalent, non-polar covalent. This is going to be a very important part of the story and another type of bond coming up later. So please, if you don't understand the differences between polar and non-polar covalent bonds, please rewind the tape and watch that part again. Okay, that's it for covalent bonds. In the next video, we're going to talk about ionic bonds, and then we're going to talk about hydrogen bonds. Okay, 2 quick review questions about covalent bonds. Why do oxygen and hydrogen not share electrons equally in a covalent bond? And then secondly, what is the term we use for that type of bond in which electrons are not shared equally? Okay, so in thinking about your answer, what would cause two atoms to share equally? It would be having a similar electronegativity. So this all has to do with electronegativity, the pull an atom has on electrons. If two atoms have a very similar electronegativity, they're going to have similar pull. Imagine that you have a very similar strength to someone you're playing tug of war with. You're both going to pull on that object equally. But if someone has a much stronger pull, they're going to pull closer to them. Okay, so when I'm playing tug of war with my dog, he's actually a lot stronger than me. And so he pulls that toy a lot closer to him. And that's what oxygen does. Oxygen is very electronegative, and that's very important to remember. Oxygen is electronegative. It means it has a very strong pull on shared electrons. And therefore, when oxygen is sharing with something not very electronegative like hydrogen, oxygen is going to be the electron hog. They're not going to share equally, and that is called a polar covalent bond. So polar is unequal sharing, non-polar is equal sharing of electrons. So here's the typed out answer for that. Okay, we'll be talking about these types of bonds again when we talk about hydrogen bonds. So we'll be talking about these again.